All right, thank you everyone for coming today. So today we have James Davies talking about geometric graphs with high girth and high chromatic number.
Thank you. So I'll start off by just talking about what are some easy ways a graph can have large chromatic number. So probably the easiest way to have large chromatic number is just to have a large clique, so a large set of vertices that are all pairwise adjacent. So for example, in this 5 clique, we clearly need at least 5 colors. Otherwise, we're going to have a pair of colors that are a pair of vertices that are adjacent with the same color. So perhaps the first interesting case to consider is if you forbid a clique, can you have large chromatic number? So we can just look at forbidding a triangle, a free clique first. And then here we have this really classic result that there are triangle-free graphs with large chromatic number. So I really want to start by getting right into it and actually showing this construction of top. So the idea here is to build up our triangle-free large chromatic graph inductively. So we can say start with this 2 chromatic graph. This is just a 3 vertex graph, clearly triangle-free. And we want to use that to build a new one with chromatic number 3 that's still triangle-free. So the way we're going to start is have 5 extra vertices. And now the idea of having 5 here is that just by pigeonhole principle, in any 2 coloring of these vertices, we're going to have 3 that get the same color. So then the way we're constructing will work to take advantage of this is for every triple. So starting with this triple vertices, we add some disjoint copy of our original graph in the previous step and add a perfect matching between this graph and these 3 vertices, like so. And this is something we'll continue and do for every triple within these 5 vertices. And next we can take these 3, add a disjoint copy of our original 3 vertex graph, and add a perfect matching. So doing this for every triple, we end up with actually added 10 disjoint copies of our 3 vertex graph, each with a perfect matching to one of these 3 element subsets of these 5 vertices. And then, like I was saying before, the way to show this as chromatic number 3 now, so there's no 2 coloring, is we go back to looking at these 5 vertices, consider a 2 coloring. By pigeonhole principle, we can find 3 of the same color. So in this case, 3 red ones. Then we look at the disjoint copy of the graph we used in the previous step that's attached to these 3 vertices. And because of this perfect matching, we see that every vertex in our original graph here is adjacent to a vertex we've already colored red. So we can't complete this coloring. We can't complete a coloring of this graph with 2 colors because we can't give any of these a red color. So that guarantees that the chromatic number goes up. The other thing we need to check is that we stay triangle free. So in this case, we know we were triangle free before. So a new shorter cycle must use one of these 5 vertices with edges to these disjoint copies. So we can look at what a cycle could look like if it contains one of these vertices. And in this case, we can see a cycle containing one of these vertices. The first edge must go into one of these copies of our original graph. And then there's only one edge coming out, going to these extra 5 vertices. So we need to stay in this copy of our original graph for the next edge. And then at that point, we can get out. And by that point, we have a path of length 3. We're at a different one of these 5 vertices. So if we want to go back, we need to again take another path of length at least 3. So actually Tut's constructions are better than this triangle 3. If you start off with a graph of girth at least 6, then you're going to maintain that you have girth at least 6. So, and by girth, I just mean the length of the sorted cycle. So with this, we can not just avoid triangles, but we can also avoid 4 and 5 cycles.
I'll interrupt for a moment. I don't know if I'm the only person, but I'm getting I guess feedback or something, which is something.
Yeah, I can hear it too. Could you try, I don't know, just muting your audio for a
volume
second?
down a bit, James. It might help.
Yes, I'll use earphones.
All right. Yes, that's a lot better.
You know there's 20 to a large chromatic number. So then it becomes interesting to ask for certain class graphs if forbidding triangles is enough to bound the chromatic number. And in general, if bounded a clique number is enough to bound the chromatic number. So we say that a class of graphs is chi-bounded if there does exist a function which bounds the chromatic number in terms of a clique number. So one way you can kind of see this is that as you go to bigger and bigger cliques, forbidding that clique and guaranteeing bounded chromatic number becomes a stronger and stronger property. Because by forbidding a bigger clique, you're forbidding less than if you forbid a smaller clique. So in that sense, if we're looking at a class of graphs where we're not chi-bounded, we can also go in another direction and ask if something weaker is at least true, where in the other direction we're forbidding more and more. So a natural way to look at this is if we look at this graph with some higher girth. So for instance, forbidding 3 clique triangle is the same as saying we have girth at least 4. So if we're not chi-bounded, or if there exists triangle 3 graphs with large chromatic number, then it will hopefully still be true that, say, if you go to girth 5, you have bounded chromatic number, or if you go to some massive girth, you eventually have bounded chromatic number. So this is really going in the other direction to chi-boundedness and hoping you still get something weak is true to ask this kind of question. And again, it's interesting to ask this for class zero graphs because in general, we know that there exists graphs with large girth and chromatic number. So I want to talk about some geometric intersection graphs. The first we'll look at is rectangle intersection graphs. So we're looking at rectangles in the plane, and we want these to be axis aligned, which just means that their sides are parallel to some axis. So you can't have any weird rotations for these rectangles. And then, so for example, this set of axis aligned rectangles, we can look at their intersection graph. So you make their intersection graph by having a vertex corresponding to each rectangle, and 2 vertices are adjacent whenever their corresponding rectangles intersect. So these rectangles give rise to this rectangle intersection graph where vertices of one color correspond to rectangles of the same color. So for rectangles in the plane, you have this nice classical result that these rectangle intersection graphs are chi-bounded. So, I mean, this is classical in studying geometric intersection graphs and this in chi-boundedness in general. This was proven before we even were using the word chi-bounded. So this is a nice strong property. And if we consider higher girth here, then we actually get something stronger than a bounded chromatic number. So we know that if you consider rectangle intersection graphs with girth at least 6, then you contain a vertex of degree at most 3 even. So you have this degeneracy and can very easily color these graphs. And this is actually also true for girth 5, just with some higher bound on the minimum degree. So with these very positive results for rectangles in 2 dimensions, we can also look at similar intersection graphs in 3 dimensions. So you can look at box intersection graphs. So again, these are intersecting graphs defined in the same way, and the boxes we're looking at are axis aligned. So again, you can't get any of these weird rotations. We're just doing translations and scaling along axes. So we could have boxes like this, for instance. And these boxes in free space will give you this intersection graph, where again the colors correspond. So unfortunately, it turns out we don't have such a nice property of chi-boundness for these box intersection graphs. And Berling showed that this triangle-free box intersection graph with arbitrarily large chromatic number. And the graphs he uses for this construction are really nice. On the other hand, another difference that was recently shown between the box and the rectangle graphs is that there exists box intersection graphs with girth at least 6 and arbitrarily large minimum degree. So we don't have this nice stronger degeneracy property when we go to a higher girth. So particularly with Berling's Berling's construction, a natural question is, well, we're not chi-bounded, but if we go to a higher girth, do we at least have bounded chromatic number? So one of the main results I want to talk about is that this isn't the case, and you can actually construct box intersection graphs with arbitrarily large girth and chromatic number. So that generalizes both of these. And you can also consider boxes in higher dimensions, of course, and this result will still hold just because you can look at some 3-dimensional part of it. But when I say box intersection graphs, I really mean in 3 dimensions, just for simplicity here. So another kind of intersection graph I want to talk about is segment intersection graphs. So here we define intersection graphs in exactly the same way, only now we look at straight line segments. So again, we can start off by looking at these in the plane. So these 5 segments in the plane will give you this intersection graph, for instance. And here already in the plane, before you even go to 3 dimension, you unfortunately have that these things aren't chi-bounded. So this is again a really nice proof showing this, and is again using Berling graphs. But on the other hand, you do still have this nice degeneracy property. So if you went to girth 5 or even just for bit 4 cycles, then you know that you can find some vertices in your segment intersection graph with some bounded degree. So this is a nice result. And then following this result, Fox and Pat's asked if their theorem could be generalized to 3 dimensions. So they asked if you considered segments in free space rather than in the plane with no 4-cycle subgraph, then do they have bounded minimum degree? And if they don't have bounded minimum degree, then is it at least true that they have bounded chromatic number? So here as well, we give a negative answer to this. And so that there's, just like with boxes, there's segments in free space whose intersection graph has arbitrarily large girth and chromatic number. And actually, mostly just because it's convenient for the proof, we do this for a subclass of full lines in free space. By the way, feel free to stop me if anyone has any questions. So I want to talk about the construction used for both of these theorems for box and line intersects in graphs with a large girth and chromatic number. So to do that, there's kind of two stages of things to talk about for it. I'll first want to talk about what the actual graphs are. And then after that, I want to talk about how you realize these graphs geometrically. So first, looking at what the actual graphs are, we're going to go back to the beginning again. So going back to task construction. And I just want to give a different perspective on this construction. So our tactic before was to add a disjoint copy of our original graph, the 3 vertex path, for every triple of vertices here. Viewing this differently, we could see this as adding a disjoint copy for every hyperedge in a 3 uniform complete hypergraph on these 5 vertices. So this is a messy drawing because there's a lot of hyperedges, but we just have a hyperedge for every triple of vertices. So there's one here, here, and we can have other ones that look like this and that. And we do this construction exactly the same way. For each hyperedge, we add a disjoint copy and add a perfect matching. And we do this for all of them. So here we're constructing the exact same graph. We're just doing it under this framework of this auxiliary hypergraph rather than using pigeonhole principle at some point. And this works in exactly the same way. If we had 2 coloring of these first 5 vertices, by pigeonhole principle, we have 3 that are the same color. This is equivalent to saying we have a hyperedge in the auxiliary hypergraph whose vertices are all the same color. And then we look at this, we've got this perfect matching to the graph in our previous step. None of these vertices can use the red adjacent vertex, so we can't complete this 2 coloring again. So this works exactly the same way. We get a 3 chromatic graph. So really the key property in using this complete uniform hypergraph was that there's no 2 coloring. That avoids a hyperedge whose vertices are all the same color. So actually, we just define chromatic number this way. Chromatic number of a hypergraph's minimum number of colors needed to avoid a hyperedge whose vertices are all the same color. So this complete 3 uniform 5 vertex hypergraph has chromatic number 3 is why it worked. The other thing we can examine is where we were getting our 6 cycle from in task construction in this way. So essentially, the reason we were getting 6 cycles and couldn't easily avoid 6 cycles here was because the hypergraph we were using had a 2 cycle. So here, this is a 2 cycle, just because we have 2 hyper edges that share a pair of vertices. So for cycles of hypergraphs, we're using bird cycles. And again, it's the reason this 2 cycle is giving us a 6 cycle here is because we need a path of a length at least 3 to go from one vertex in our hypergraph to another, and that has to be contained in the same hyperedge. So if we have a 2 cycle, then we can end up finding a 6 cycle in the actual graph we're constructing. So one thing we want to do if we want to do better in girth 6 in general with this hypergraph variation of task construction is we want to avoid at least 2 cycles in the hypergraph. So I just want to talk a bit about hypergraphs now. And because this is graph and matroids, can look at the Fano plane. So we can get a nice hypergraph on the Fano plane. So we have these 7 points, which we have to get vertices from. And then for each 3-element circuit, we're going to have hyperedge. So we get a hypergraph from the Fano plane, like so. And then one nice property here is that any 2 coloring of these vertices, you can find a hyperedge. These vertices all contain the same color. So here, for instance. But if we use 3 colors, then we can avoid any monochromatic hyperedges. So this is just saying that this Fano plane hypergraph has chromatic number 3. Another nice thing is that unlike when we're using just uniform complete hypergraphs, is that we now avoid 2 cycles. So this Fano plane doesn't have a 2 cycle, just because there's no 2 hyperedges that share a vertex, share a pair of vertices. We do, however, have 3 cycles. So here, there's a 3 cycle in the hypergraph, and here by cycle in hypergraph, we just mean we have a alternating sequence of vertex, hypergraph, vertex, hyperedge, vertex, hyperedge, vertex, hyperedge, and back to vertex. So the idea is now that we've at least avoided 2 cycles, when we go through and use a hypergraph like this in Tuts construction, we shouldn't get 6 cycles. And in general, the idea is that if our hypergraph has large girth, then we should avoid more cycles. So the graph we're constructing will have high girth, or maintain a high girth rather. And then the other key property was that our graphs were 3 chromatic, hypergraphs were 3 chromatic, so had no 2 coloring. So really what we want to use in this variation of Tuts construction is uniform hypergraphs with large girth and chromatic number. And we know that these exist. So I just want to go through and demonstrate this variation of Tuts construction one more time. So this time we're using the Fano plane to go from our 3 vertex path to get a new graph. And this time we're going to have higher girth than 6, and we'll still go up to chromatic number 3. So instead of doing every triple vertices and adding a disjoint copy of our original graph, we're going to do the triples that are contained in one of these hyperedges that contain 3 vertices. So we add this for each of these. This hyperedge, we add a disjoint copy of our original graph, have this perfect matching. Same for this hyperedge, same for this, and same for all the others. And now, already seen this before by this point, but you can see how this works exactly the same again. If we had 2 coloring of the vertices of this auxiliary Fano plane hypergraph, then we can find 3 vertices, all in the same hyperedge that are the same color. These 3 red ones, for instance. And then we look at the copy of our original graph, which we attach with a perfect matching to the vertices of this hyperedge. And again, these are all adjacent now to a red vertex. So we can't complete this coloring with 2 colors because we can't use red here. So that increases our chromatic number to 3. The other thing is that now that we don't have 2 cycles in our hypergraph, we're not going to get 6 cycles. So actually, in this case, the shortest cycle we can find is one of length 9. And this just emerges from a 3 cycle in a hypergraph. So we'd get it to look something like this. Necessarily, we must have a 3 path between each pair of vertices in the same hyperedge. to go back to vertices of the auxiliary hypergraph. So from a 3-cycle in a hypergraph, we could possibly get a 9-cycle graph we construct. And in general, this continues the same way. If we're using hypergraphs with girth at least G, say, then we can maintain in our graphs a step of this construction that we have girth at least 3G. So essentially, the graphs we're using is this kind of hypergraph variation of Tut's construction. But one important thing to consider with this is exactly what hypergraphs we take, which will be the next thing I want to talk about. So here we really want to take a very special kind of high girth, high chromatic hypergraph. So the next thing I'm going to talk about is leading towards that, but at first it may almost look like I've just forgotten about what I'm talking about and decided to talk about something else nice and pretty I like, but that's only half true. It is nice and pretty, but it is going to come back around and be helpful. So a definition for that first. So we say a homophytic map is one where we have uniform scaling and a translation. So for example, this purple star, we can have a homophytic copy being this blue star because it's obtained by uniformly making it bigger and translating it over here. An example of something that's not a homophytic copy is this red star. And that's just because we've scaled it in the vertical direction, but not horizontal. So the scaling here is not uniform. So this isn't a homophytic copy. Another thing that's not a homophytic copy is this star. We've done uniform scaling, but we've also done this rotation, which we're not allowing. So in general, homophytic copies are just ones obtained by uniformly making them bigger, uniform scaling, and the translation. So now there's this really pretty theorem, Galois theorem, that if you finitely color the points in d-dimensional space, then if you pick a finite set of points t, you can always find some monochromatic set of points that's homophytic to your chosen points t. So I think this is really nice. So a classic, I think the classic example for demonstrating this theorem is that if you have some coloring of the plane, then you can always find 4 points of the same color that are the corners of some square. So for example, I have some very artistic coloring of the plane here. And this theorem says that I can find 4 points in this example here, here, which are the corners of some square. Just to make it more clear, it looks like this here. So I think this theorem is really nice. Another theorem that may look more familiar is van der Waals theorem. So van der Waals theorem says that if you have some finite coloring of the integers, then you can always find arbitrarily long arithmetic progressions. So one way to see that this is related to Galois theorem is if we're looking at a one-dimensional version of Galois theorem, so just in the reals, and for a set T, we pick 3 evenly spaced points, then what Galois theorem is saying that is for any finite coloring of a reals, we can find this 3-term arithmetic progression. So you can in fact say that this one-dimensional version of Galois theorem is essentially equivalent to a multi-dimensional van der Waals theorem, and then in turn you can say that Galois theorem in general is essentially the same as a multi-dimensional van der Waals theorem. Anyway, I was talking about hypergraphs and stuff before, and this stuff sounds pretty different. So I need to start making this look more relevant next. So we can view Galois theorem in hypergraph in a way as a theorem about coloring hypergraphs. So we can define a hypergraph from the points in d-dimensional space and some finite set of points t in there by, for each point in d-dimensional space, we have a vertex, and for each homothetic copy of our finite set t, we have a hypered whose vertices it contains are just the vertices that correspond to points that this homothetic copy of t contain. So for an example, if we're just looking at 5 evenly spaced points, say for this in a real line, and our set t is these first 3 evenly spaced points, so like a 3-term arithmetic progression, then the hypergraph we get for these points, which we can say are just 1, 2, 3, 4, 5, are the 3-term arithmetic progressions among the integers 1 through 5. So, for example, this first one, we have this hypered for arithmetic progression 1, 2, 3. We have another hypered for 2, 3, 4, another for 3, 4, 5. And then in this case, we have one more where we have a bigger gap, so 1, 3, 5. So here we've done some uniform scaling. So now we can just give a rephrasing of Galois theorem in terms of finite hypergraphs. So the equivalent theorem is that if we pick a set of a finite set of t points in our d-dimensional space, and we pick some positive integer k, then we can choose some finite set of points, x in our d-dimensional space, and then the hypergraph with vertex set x and hyperedges on x corresponding homothetic copies of t, well, should have chromatic number at least k. So this is just an equivalent version of Galois theorem stated in terms of hypergraphs and made for finite hypergraphs. So this is looking more relevant now. Like it's at least a theorem about high chromatic hypergraphs. But one issue if we want to get these box and line intersecting graphs with large girth and large chromatic number is that we need these hypergraphs to also have large girth. So for an example of where we might not necessarily obtain this is if we're again looking at these 3-term arithmetic progressions, then the 3-term arithmetic progressions 1, 2, 3 and 2, 3, 4, these hyperedges are going to form a 2-cycle. So this currently only gives large chromatic number and not large girth. So what we really want is a high girth, kind of sparse version of Galois theorem. And this is something we have. So kind of the exact theorem we want. So if we pick a set of t points in d-dimensional space with at least 3 elements, and we pick some g and some k, then we can find some set of points x again in d-dimensional space, so that the hypergraph we get has girth at least g and chromatic number at least k. So the requirement of having at least 3 elements is a more technical one, because if you're looking at 2-term arithmetic progressions, then you're going to end up with a complete graph if you just have some set of integers. So it's just avoiding some trivial case where it's not true. So the hypergraphs obtained from this sparse Galois theorem is the hypergraphs we want to use. So we actually only need a one-dimensional version in our application. And if we don't care about our graphs having high girth and we're just happy with girth 6 or even just triangle 3, then all we need to do is use Galois theorem. So the next thing I want to do is talk about how to realize these geometrically, these box intersects and graph first. So we're going to start off the same way we did in this variation of touch construction, and I just want to show you how you go from this 2 chromatic 3 vertex graph. That's just a path to a bigger one, that's chromatic number 3. So we can represent this 3 vertex graph pretty easily as intersects and graph of 3 boxes, like we do here, for instance. And we want one additional geometric property of these boxes, which is that these back corner sides, we want to lie on some additional vertical plane we've added here. So from another perspective, the representation we start off with is going to look like this. Now from here, what we want to do is use these back corner sides that lie on this plane. And for each one of those, we're going to add a line that extends outwards from our boxes and up vertically through this plane. So these are lines, not boxes, so they're not going to be part of our intersection graph or anything. We're more just using these yellow lines here as scaffolding to help us make what we need. So from another perspective now, we're looking up at our boxes from above. And in particular, we can look at this one-dimensional horizontal kind of split of this plane. So now on this one-dimensional horizontal part, these lines will just be yellow points. And for convenience, I've just made it so that these 3 points are going to be evenly spread. So now on this horizontal cut here is where we're going to use Galois theorem. And the set T for the homothetic copies we're going to look at is exactly these 3 yellow points on the horizontal line. So now we get this auxiliary hypergraph, and for each vertex, it's a point on the real line, and we're just adding another yellow horizontal line for now. So I've done this with just 6 vertices for the example. You would need more for this to actually work. You need at least 9 for van der Waals to work for 3-term arithmetic progressions, for instance. But I don't think my computer would survive if I tried 9. So we're sticking with 6 for the drawing, just to make it simpler as well. So we want to continue the same way we were in touch construction now. So we'll worry about the actual boxes that correspond to the vertices of this auxiliary hypergraph later, and just use these yellow lines, which are that scaffolding, and each line corresponds to one of these vertices in the auxiliary hypergraph. The next thing we want to do is add disjoint copies of our 3 vertex graph. So these 3 boxes, one for each homothetic copy of these 3 points on this horizontal line. So one for each 3-term arithmetic progression for these numbers 1, 2, 3, 4, 5, 6. So from another perspective, it looks like this. And when we add more, what we want to end up with is something like this. So we started with one that was just 1, 2, 3, looking at these yellow lines. And then we add the easy ones that are just translations. So 2, 3, 4, and 5, 4, 5, 6, for example. And we obtain these disk translations along the plane. And one extra thing we want to do is do a translation vertically. These vertical translations are just to make sure that all these different homomorphic copies are disjoint. So we have no edges between these disjoint copies of our original graph. So then, as well as these simple ones like 1, 2, 3, we have these 3-term arithmetic progressions of gaps like 1, 3, 5 here. And again, we just get these new copies by extending some homomorphic map of the homomorphic map in one dimension from that takes 1, 2, 3 to 1, 4, 1, 3, 5 rather. So this looks good so far. We have a copy of our 3 vertex graph for each hypered in this auxiliary hypergraph now. The next thing we need to do is add the vertices for the auxiliary hypergraph. So we can add these like so. So here we're just adding these thin, tall, purple boxes close to where our yellow lines that we're using for scaffolding. So we just make these intersect every box that was touching the yellow line. And like with all these homomorphic copies, we also make sure that these back corner sides of our boxes lie on the plane. So at this point, in terms of getting to the next step in our graph construction, we're done. We have a box that corresponds to a vertex of each vertex in the auxiliary hypergraph we're using. And for each hyperedge in the auxiliary hypergraph, we have this triple of boxes for a disjoint copy of our original graph. The only slightly technical thing to worry about for continuing this is that we want these back corner sides for there to not be 2 boxes where their back corner sides are on top of each other. But we just fixed this with minor translations of boxes along the plane. So that way, if we want to continue this, then we do exactly the same thing again. For each back corner side, for the back corner side of each box, we add a line and extend it out through this plane. And we continue this in exactly the same way. We now just have a bigger set of yellow points when we look at this one-dimensional horizontal cut. So a bigger set of points to apply Galileo's theorem to. So any questions on this construction? Okay, I'll continue then. So I just wanted to mention, it is perfectly possible to, in this construction, essentially hide this use of hypergraphs. And if we're careful, then in fact, all we need for the case of boxes is to use a sparse van der Waals, or even if we only care about triangle 3, just plain van der Waals theorem, rather than Galileo's. But I think it's nice to see the actual graph perspective from this hypergraph variation, because I think there can be constructions for particularly other geometric lasso graphs where you really care about taking some other high girth, high chromatic number hypergraph, and these hypergraphs could be special hypergraphs you take from some different kind of theorem. Okay, so lines. I want to go through the construction for this, and a lot of it's going to be the same. We aim to use Galois theorem or a sparse Galois theorem to build up more lines in the same way that we did for task construction. So a lot of what you'll see here is pretty similar to what you just saw for boxes, but some of the geometric arguments are slightly different. So I think it's good to see one for the slight differences and two to see the same thing again. So again, we're going to start off with our 3 vertex path, which by now is my favorite graph. So we have intersection representation for a 3 vertex path with these 3 lines. And now the next step we do is take some plane that intersects these 3 lines. Now, in this plane, for each intersection point with a line, we want to add a new line, which is vertical in the plane and intersects only the single line. So this is going to look like this. So this time these lines we've added are lines we're adding for the intersection graph. It's not the scaffolding. These are going to be vertices of the graph we're going to get. And now, looking at above, we're going to do a same tactic. We look at this one-dimensional horizontal cut of this plane. This again are arranged nicely to have 3 evenly spaced black points. And we're going to apply Galois theorem or sparse Galois theorem again to get points on this real line here, whose hypergraph has large chromatic number and large girth. So I'm going to do it, so how this goes if we just had 5 lines this time. So these 5 lines will be the vertices of our auxiliary hypergraph. And these 3 lines are the vertices of one of our disjoint copies. So again, we want to add, for each hyperedge here, we want to add a new copy of our original graph joined by this perfect matching. So we add these like so. So again, we're just looking at homophytic copies of integers 1, 2, 3 and the integers between 1 and 5. So we should have 4 copies of our original graph in this picture here, one for 1, 2, 3, another for 2, 3, 4, another for 3, 4, 5, and one more spread out one for 1, 3, 5. If you want to challenge, try and find which one that is. So at this point, we're done in terms of getting the next graph in our construction. The only thing we could be worried about is how to continue this construction to the next step. But we just do this the same way. These are infinite lines here. So we can take some plane that intersects every line, like so. And from another angle. And then we're just going to continue our construction exactly the same way. We'll take some kind of lines that intersect each one within this plane and continue with another application of Galois theorem. Okay, so before I end, I thought I'd mention a couple of problems, and we'll just focus on these box intersection graphs for now. So one natural question is, how small can they be? So we're repeatedly using this sparse Galois theorem or sparse van der Waals theorem, and already the bounds on van der Waals theorem are necessarily pretty big. And we're doing this at each step to increase the chromatic number by 1. So with disk constructs, and the size of our graph is necessarily, well, the size of the graph we get is enormous. There is another recent result that shows that you can, that gives a good bound for colorings when you forbid a 4 cycle. So although in general you could need arbitrarily many colors from this theorem, we do know if you forbid a 4 cycle and you have n vertices in the box intersection graph, then you have a vertex of degree at most the order of log n to the 9. So these graphs do have to be big, but you wouldn't think as big as the ones I'm showing. So another question that I think would be nice for these box intersection graphs is based on the old really fundamental conjecture in chi-boundedness. So Glyphosate summary conjecture says that for every tree, the graph with no induced copy of T, of your tree T, is chi-bounded. And then just bearing in mind that forests are induced subgraphs of trees, this is really, would be a really precise statement if true. Because essentially the only graphs you could forbid one single graph of and hope to be chi-boundedness is trees. Because if you forbid something with a cycle, then we know in general that you have graphs with object large girth and chromatic number. So with this new theorem, I think box intersection graphs become a really interesting spot for trying to prove this conjecture for at least this class of graphs. Because again, we have this precise thing where trees are really the only one graph you can hope to forbid and become chi-bounded. I'll stop there.
Great, thanks, James. So we haven't usually done applause in the past, but I'd like to today. So let me give everyone a second to unmute themselves. Maybe I should actually look at the list. All right, let's give James a round of applause. Got some virtual claps too. All right, so are there any questions for James?
Does the, if you're looking at the ratio of the longest and shortest sides of your boxes, does that go to infinity as girth and chromatic number go in your construction?
Yeah, pretty quickly.
Is that necessary? Could you do it with that bounded?
I don't think that's possible. It probably depends on the object, actually. But my guess is in general, you can't. I'm not sure if there's a result for that. Rose might know this one.
Sorry, what was the question?
If you forbid, go on.
If I think that really long skinny boxes are cheating, like if you're not
Yes, so if the aspect ratio is bounded, then the class is chi-bounded.
okay.
Yeah. So, one nice thing that Jim pointed out is that you can make it so that the top and bottom faces of these boxes are squares. But I think you do need at least one part that goes.
It was actually Rose's observation, but yeah.
Oh, okay.
But now that I look at it again, I'm not sure how to do it, so I'd like to talk to you about it.
Some people said some things and someone got it.
Right. Are there any other questions? All right.
Think about the ratios that you mentioned. Is that true if you have just something like some sort of scaling, like if there's a ball inside and outside, does it have to be like, is that to do with boxes or is that a very general result?
I guess for connected convex sets, it holds. Maybe you can go a little bit further than that, but definitely.
Connected convex sets where you've got like a ball inside or and then some scaling outside or something like that. What does the result say?
So if for every point in the shape and for every ball centered at that point, if the volume of the ball intersects the shape is at least a constant fraction of the volume of the shape, or is at least the volume of the ball if the ball's too big. Sorry, is at least the volume of the shape if the ball's too big. Maybe we can talk about it later. All right, I'm going to stop the recording.